Welcome to our webinar. We here at Standard Imaging know that your time is precious, particularly during these challenging times. Standard Imaging is proud to be helping with your radiation calibration and quality assurance needs. It's your time. Be precise. My name is Mary Napolitano, and the topic for today's webinar is, what have your log files done for you lately? Standard Imaging has a Logfile-based patient plan QA solution, LinacView, that provides enlightening information concerning your plan delivery. Thank you for taking the time to share your coffee break time with me today. So let's go over a bit of housekeeping. Today's webinar will be recorded. Please enter questions at any time during the presentation in the GoToMeeting dialog box. I will answer all questions at the end of the presentation. Standard Imaging is based in Middleton, Wisconsin, and founded in 1989. At Standard Imaging, we design and manufacture a full suite of QA products. During my presentation, I will begin with the basics of log files for those not so familiar, then move into the basics of RTPlan files, so that consideration and comparison at a very high level can be reviewed between the RTPlan file and the log files. There are lots of details involved, and so we will only touch on things at a very high level. Finally, I will finish up with some specific comparison mechanism available within LinacView. Here's the basic information flow for LinacView. The RTPlan is exported from the treatment planning system, both to the through to the LinacView computer, as well as to the Linac console. For any plan already imported, LinacView automatically matches log files that are synced from the Linac for comparison to the plan and analyzes numerous parameters. So log files were initially generated, as log files are for any software, to record the delivery based on the feedback mechanism designed into the Linac and primarily used by Linac engineers. The MU, positioning of each MLC, jaws, gantry angle, collimator are recorded. When the parameters, for whatever reason, exceed tolerance, as designed, beam off occurs, and in some cases, beam on will resume once parameters are back within tolerance. We are interested in collecting, or really accessing, the Linac log files during all deliveries. This is easy with Varian TrueBeams because the trajectory log files folder is an open access folder. It's slightly more complicated for the Varian Linac because the Dynalog folder is openly accessible and is not openly accessible, and you will need to install a tool to duplicate this folder into an accessible folder. The Elekta log files are more complicated. For read-time access, we are required to use their ICOM VX interface to write our own files based on the data stream from ICOM VX. And we do not have access to the TRF log files. So log files can be used to make direct comparisons of multiple parameters. And so what exactly do they contain? Parameters such as the jaw positions, carriage positions, each MLC leaf position, gantry collimator angles, monitor unit, as well as beam off states with beam hold, meaning hold on or off. For example, Elekta Linacs do not entirely beam off in most cases during delivery, but instead reduce the dose rate. We also have table positions and angles. From these parameters, one can then directly calculate the delivered fluence as recorded by the LINAC. The same calculations can be performed based on the RTPlan such that direct 2D fluence can be analyzed. This direct analysis is highly sensitive to catching induced errors. Both Elekta and Varian save similar results to log files. So next, how often does this sampling occur? All of the parameters listed in the previous slide, with the exception of the fluence, are directly logged at a uniform frequency. The sampling rate, meaning the number of data records per second, varies for the different log file types. The older Varian LINAC series samples at 20 records per second and saves Dynalog files. The Varian TrueBeam samples at 50 records per second and saves trajectory log files. Elekta provides slightly different recording options. TRF files, which are generated 25 records per second, but unfortunately, as I already mentioned, these are not made available for real-time usage by external vendors. These files can be manually exported after planned delivery. The other option from Elekta is using the Icon VX interface. The sampling time here, though, is 4 records per second, which is problematic, for example, during startup, but is still more than suitable for static analysis, such as a composite fluence comparison that I mentioned earlier. The sampling rate for the other 3 files are quite good. We would like to be able to access the TRF files from Elekta LINACs. All of these files contain a wealth of information. The question is, are you making good use of the data in your clinic? So here's a Dynalog file specification for each column being a record, starting from left to right with the beam off state, 1 being on, 0 being off, and moving across, or here it's down the way it's listed, to the MLC expected and actual positions for each leaf. And then I'll show a specific example. And here they actually are across, starting with the beam hold or beam on state and moving across to each leaf expected versus actual position. So here for the Dynalog files, there's no direct mapping to control points. The dose fraction must be determined based upon the current dose fraction and the prescribed MU, as shown in this equation. And so at this point where the red line is, 13.2 of the total 150 monitor units have been delivered. And parameters here, each row designates 50 milliseconds. Next is a sample of a trajectory log file. This type of log file is much easier to map and match to the RTPlan control points. There's a direct fractional control point mapping, and as well as fractional MUs. And here each line is specified on a 20 millisecond increment. And you can see the types of parameters that are logged. So once one understands the information coming from the log files, the next step is to be able to map the log file records to the RTPlan control points. We can even generate RTPlans with different numbers of control points that may map the actual delivery more closely than the delivery presented by the treatment planning system. So the RTPlan specifies delivery based on control points. Only at these points is the configuration specified. And between the control points in the treatment plan, the leaf movement and monitor unit is not specifically defined, so one can't be sure, other than the assumption one makes that it's linear between control points. As well, the LINAC control system may make adjustments to some parameters as part of the delivery process. So how do we find the control points in the RTPlan? Because we need to map those to the log file. So I'll go over a bit of an overview here. There are many free DICOM viewers in case you haven't ever taken a look at your DICOM files. So there's a DICOM tag which corresponds to the different named attributes and values, which you see in these columns. There's descriptive information, but down here is the important information under the beam sequence. And so if one expands this area under the beam sequence, there you can see that there are 4 beams for this plan. And under each beam is a control point sequence area. And so expanding again here under the control point sequence, one sees the control points that we're looking for. So beginning with control point 1 at the top, you can see specified the positions of the X and the Y jaws. The MLC positions have to be expanded out, so you can't see all of them, but they're under this tag. The gantry, collimator, couch angle, fractional MUs, and these are the familiar parameters outlined in the log files as well. So compared to control point 1, if one reviews additional control points, you can see there are many less parameters. For example, the couch positions, because those are not changing, because quantities whose values don't change are not repeated in subsequent control points. In this case, you can see that the gantry angle moves clockwise from 358 to just over 1 degree. And the fractional increase in monitor unit is from 0.497 to 0.502. And then finally, if you move down to the last control point, you can see that the monitor unit fraction is complete and of course is specified as 1, and your gantry angle stops at 179 degrees. And so, with this information about the control points from the RTPlan and the log file, how do we go about mapping those together in LinacView? So for the Dynalog file, I'll go ahead and give some description. So the RTPlan control point is positioned, and these are the RTPlan control points on the bottom, in the center, in the middle of the interval between 2 successive log control points, and these are the log control points at every 50 milliseconds. The prescribed value of the parameters linked each log file control point is obtained by linear interpolation between the 2 prescribed control points contained in the 2 successive RTPlan control points. So the worst case uncertainty in positioning for this case is 25 milliseconds. One can see a concrete example in the lower right when reviewing a chart from LinacView for gantry angle deviation versus RTPlan control point. So this is gantry angle deviation versus RTPlan control point, and the red line designates the failure, and the orange line designates an alert. So the prescribed value of the tested parameter links to each control point is again with the trajectory log file obtained via interpolation between 2 prescribed points in the 2 successive RTPlan control points. And you can see here again the mapping. The uncertainty of the link between the log control point and the RTPlan control point, and by consequence, the uncertainty of the prescribed value are negligible because the linked RTPlan control point is close to the actual real number. So then the study of the deviations between the delivered and prescribed really has next to no distortion. And similarly, one can see negligible distortion when reviewing a chart from LinacView for the gantry angle, again, the gantry angle versus the RTPlan control point for a particular plan. As well, we can do fluence comparisons between the RTPlan and the log file by projecting the MU weighted segments. In this case, the gamma 2% 2 millimeter with a threshold of 5% has a calculated pass rate of 99.7%. Similarly, I'll show an example from a trajectory log file. The LinacView fluence map comparisons are shown with 100% pass rate for a gamma of 2% 2 millimeters with a 5% threshold. In general, good results are not surprising, as there's no setup uncertainty, no finitely spaced detector grids, etc. And so, as time is limited, I'm just going to go through one case during our short coffee break. And I'm going to go ahead and switch over to LinacView. It's a head and neck case, and I'm going to show you it has a single arc, and go ahead and move over to the software. So this is the LinacView dashboard. And as you can see, it's completely empty at this point because we haven't started any delivery today. And so what I'm going to do is go ahead and send some log files into the LINAC. Previously, the RT plans have been exported to LinacView as well as to the LINAC itself. And so we're going to pretend like delivery is starting. And you can see there are 5 different sessions, and the import is occurring. The analysis has already completed for the first session. I'm logged in as an administrator, and so I see a lot of additional information. So in one of the columns, it's showing fail, but if I were a therapist, I would be logged in and I wouldn't see all of these columns. And so the therapist or the person at the console would only have a view of the pass. And so you can see in that very short amount of time, 5 different sessions, daily sessions were analyzed. So we're going to go ahead and load the session that had the alert. And then I'm going to briefly go over some of the details of LinacView. You'll notice that in the dashboard, everything is color-coded. So it brings your eye right to the parameters that you want to review further. Green, of course, is passing. The orange color is an alert, and red, of course, is failure. And so there are many parameters here. You can look at the jaw positions, the RMS error versus the maximum, summaries of all sorts of parameters, the leaves, the integrated fluence map comparison. You can see the results. But in particular, we want to key in on this gantry because it's in the orangish color. And so we can go over. And one can see that at the very beginning, the alert level was exceeded. And this in particular is an older LINAC where there was a drive chain tension issue. As well, one can look at additional information, the monitor units versus the RTPlan control points that we looked at earlier, the plan, the log file versus the plan fluence. One can look at that. This is plan versus delivered, the absolute fluence deviations, as well as the gamma comparison map. And then as well, it's always fun to look at the dynamic view of the plan, where one can see positions in red where the leaf position is either a fail or an alert. One can see when the beam is on and off, the gantry and collimator angles, and then in this quadrant, one can see the fluence map comparison at all times. And if it's gray, it's within tolerance. And if you see it portions that are red, that exceeds tolerance on the high side, or green, tolerance below on the lower side. And so you can watch the delivery of your plan, look at all the leaf positions, and it'll show if they're too open, too closed, the expected and the deviations at all times during the delivery. So there's a lot of interesting information that one can see within LinacView. So since we're a bit time constrained, I'll return to our presentation, and if anyone would like to see the software in more detail, don't hesitate to reach out. And so now back to the presentation. And so that demonstration was at the point in which the RTPlans had been exported, and then the log files from the LINAC were brought into the software. So I wanted to next go over some recent publications, just to give you an idea of what's been published recently. I know in the past there have been a good number of publications comparing EPID leaf positions to Logfile leaf positions, and then more recently there have been numerous publications comparing Logfile analysis to detector arrays. And so these are some publications that came out in last month's Journal of Applied Clinical Medical Physics. And then this is from this past year's AAPM, a poster presentation. And the Logfile solution is found to be, and I quote, very sensitive in detecting small delivery errors. Logfile analysis, to quote from the third article, provides a robust and reliable QA method to reduce patient-specific QA measurement, provided that a comprehensive measurement-based machine-specific QA program is in place. And that's a very important detail. So you must always have your machine-specific QA program in place. And just in general, I'll have to say these types of analysis programs provide an end-to-end plan transfer as well as beam delivery checks. And so now I'm going to take just a few minutes to go over some of the data in this first presentation. So this is a poster from AAPM entitled An Investigation of Using Logfile Analysis for Automated Patient-Specific Quality Assurance for an MR LINAC. So for this study, 66 plans were delivered on an Elekta Unity. These plans were also analyzed with a detector array as well as LinacView. 11 of the 66 plans were incorrectly matched to check for error detection sensitivity. And just a step back, so with the Elekta Unity, each plan of the day is optimized when the patient is on the table. So they were focused on correctly matching the day's RT plan to what was being delivered. And so the gamma, 3%, 3 millimeter for the correct plans, there were 55 of those, was around 95% for both methods analyzed. Or I should say between 95 and 100% for both methods analyzed. For the incorrectly matched plans, the detector array showed between 3.9% to 8.4%, while LinacView was more sensitive to error with gamma pass rates in the range 1.2% to 21.7% for the same plans. The poster states that, and I quote, "The log file analysis can provide higher throughput due to automation, but can also provide faster patient-specific QA feedback to clinicians and physicists." So in summary, I hope that I have convinced you that there is a wealth of information available for analysis within your log files. LinacView software maps RTPlan control points to log file data. Comprehensive analysis tools are available, and I showed you just a few of those. Log file analysis is more sensitive to detecting errors compared to detector arrays. And so that concludes my talk about what have your log files done for you recently. If you have not already done so, please type any questions that you may have into the GoToMeeting dialog box. For more details on any of these solutions or for a comprehensive software demonstration, please feel free to reach out to me or your sales representative. Also, you can find additional Astro Series webinars on our website at the address shown on the slide. I'm going to take a quick look and see if there are any questions. So the first question I see is, do you have an agreement with the LINAC vendors to access the log files, or is it the user's responsibility to have the license with them? So as I mentioned before, for the Varian solutions, one of the types of log files is collected in an open folder that you can have free and easy access to. The other type of log file, we just duplicate that folder, and so that we can access it real time. And then on the Elekta side, we actually vendors are allowed to access the ICOM VX data stream coming from the LINAC, and that's the recommended method from Elekta to access the data coming from the LINAC. And so that is freely available. As I understand at this point in time, there is no extra charge for that. And so we do then have to create our own log files from the ICOM VX data stream coming from the LINAC for Elekta. And that is the only question that I see at this point. So I thank you for your attention, and have a great rest of your day.